Is entire screen coming there?
Good evening, everyone. Sorry for the delay. Welcome to another session of CNI seminar series. Today's talk is by Kumar Saurav, and he will be speaking on online age of information scheduling. Kumar Saurav is a PhD candidate in the School of Technology and Computer Science at the TIFR Mumbai. His research spans online His research spans online scheduling and resource allocation problems in networks and computer systems. His PhD results on online age of information scheduling have appeared in reputed conferences and journals, including IEEE JSAC, IEEE JSIT, Performance Evaluation, and IEEE Infocom, and were showcased at Graduation Day Forum, IEEE SPCOM 2022, and ACM ARCS 2023. He has also been a finalist at Swachhathan 1.0, a contest organized by the Ministry of Drinking Water and Sanitation for his solution for monitoring the usage and societal impact of public sanitation infrastructure in rural India. Before we move on to the talk, we would like to request the online audience to keep your microphones on silent. Please unmute yourself and ask if you have any questions. Over to you, Kumar sir.
Yeah, thank you. Thank you for kind introduction. So yeah, today I will be discussing parts of my PhD research, uh, which I carried at TIFR Mumbai. So this will be all joint work with Professor Rahul Baze. Um, so broadly, like consider these modern applications such as this virtual reality, tele-robotics, etc. In such networks, in such applications, we usually have a source and a monitor, and it is required that at any time the information at the monitor should accurately reflect the most recent state of the source. So this is called information freshness. So naturally, this has to be achieved by transmitting a sequence of updates from the source to the monitor. However, here the emphasis is on the information at the monitor instead of the individual updates that the source transmits. So that is why this problem is the scheduling problem pertaining these applications are very different compared to what we usually have been doing in classical problems. And hence, these new approaches have been developed to quantify the requirements of these applications, or in particular, this information freshness. One is using this age of information metric. So basically, for this information freshness, age of information metric is a metric basically to quantify the requirements and evaluate the performance. So today we will be like discussing the scheduling problems pertaining this age of information metric. So before going there, we'll just look at what is this age of information in a little more detail. So like consider a source monitor where at the source, updates are generated at certain time instance. Say an update is generated time G1, which it transmits and it is received at the monitor at time R1. Another update G2 is generated at time G2, which for some reason is not received at the monitor. Then another update at G3 is received at time R3 and so on. So at any time T, look at the most recent received update and look when it was generated. The difference between the current time and the generation time of the most recent update, that is the age of information at time T. And so basically, this is the current time minus the generation time of the latest received update. So by very definition, this age of information increases linearly with time unless a new update is received, at which point this age of information decreases to a value which depends on the generation time of the received update. And then it again increases linearly and so on. So basically this age of information is quantifies at any time how old the information at the monitor is, right? So this is the definition of age of information. So any doubt I would like to address at this point. Okay. No, no. I mean, that impacts the age of information. If for a packet, the latency is large, age of information, again, it's not directly related. Uh, because I will come to that difference. Because if you are, for example, this second packet is not transmitted at all. So its latency will be, you can say, infinite, something like that. But that does not affect age of information. But in certain cases, the packet that is received, if its latency is large, its age of information would be larger as well. So they are related, but they are not the same. Latency for the entire frame, I guess. Yeah, I mean, there you consider this entire frame as one packet. I mean, it will have these, each pixels will be a sub packet or something like that. But yeah, you can consider this frame as one unit. So when that frame was generated and when that entire frame has been received at the monitor is something like that. Does that make sense? Yeah, yeah. That is the biggest difference, which actually makes it uh, like more fundamentally different from the prior works. Okay. So For information freshness, we want this age of information to be small. One could say like equivalently that you can minimize this average age of information for information freshness. So this basically means that you want to minimize the area under this age of information plot that you are getting here. But naturally, when the packet has to go through a network, there's like several list of issues that can happen, because of which we need we have like certain scheduling problems, very interesting scheduling problems, and which we look forward to address. So in this talk, I will be considering a generic network where this different multiple sources are trying to minimize this age of information by sending their packets to a common monitor. However, before going there, I will start with a simple network where we have a single source monitor just for motivation. So we have a source monitor pair. At the source, these updates are generated at arbitrary time instants. These generation times are revealed causally. So when they arrive, you know that, okay, so this packet has come, but you don't know when the next packet will come. And also these updates have arbitrary sizes. Um, by size, we mean uh, because by sizes are in bits naturally, but we assume here that you are transmitting at a fixed, basically energy power. So basically, with this size update sizes, we mean the time required to completely transmit data. So basically, at arbitrary time instance, updates are generated, and updates have this arbitrary sizes. That means how much time you need to completely transmit them. And also to transmit them, we assume that you consume energy at a fixed rate C per unit is transmission time. And the sizes are also revealed at the time when the update is generated. So when update is generated, you know how much time that update will take for transmission. So at any time, what the source can do is it can choose which update to transmit. And it can also preempt an update if it wants to. Okay? And the objective here is to minimize the sum of this age of information as well as the average energy cost. Yeah. So this is basically an online decision problem. You have packets coming at you, like, and they have the different sizes, and you need to choose which update to transmit or not to transmit, because there is also energy cost. No, I mean, we assume that when you transmit, you are transmitting at a fixed rate, uh, fixed bits per second, whatever. Yeah, but that is a different work, which I am not considering here. So we have also considered that that is a different work, not part of this model. Um, so, so we have seen this model. Now we have also in past seen this response time minimization problem or latency minimization or flow time minimization. So here we have something similar, some similar model where and the goal is to minimize the mean response time. Basically, for each packet, the mean response time is the difference between when they arrive and when they are received at the point. And you want to minimize the average of this across all packets that are generated. And for this, we know that this SRPT, the shortest remaining processing time, this is the algorithm that at any time transmits the packet for which the size, that means the remaining time for transmission is minimum. So it transmits that packet at that time. And this algorithm is known to be optimal for response time minimization. So does that work for our problem? Actually, no, because these two problems are very different. Because in response time minimization, all packets need to be transmitted. While in the problem that we have considered here, it is sufficient to transmit a subset of updates. For example, if too many updates arrive in quick succession, you certainly don't transmit all of them. And yeah, so as we saw here, that you can drop a few updates, and you can actually use this feature to maybe save energy if you have like fast arrival rate. Yeah. And this makes sense actually, because for example, the virtual reality example that I showed you. So packets are coming at, the sensors are generating at a different rate, and it is coming at the VR platform at a different rate. And the VR platform can sample it, needs to sample it, which update to sample, because it can't read all the updates. It has different like computing capacity or rate that it needs. So it is important to transmit a subset, choose which subset of updates to transmit. And because you are transmitting subset of updates, the energy here depends on which update you transmit. So that also depends on the policy. While in this response time minimization, because you are transmitting all the updates, you are basically transmitting like, and sizes of updates are fixed. So you're transmitting, all policies transmit like equal number of bits and consume equal power. So because of these differences, what we see is this SRPT is optimal for response time minimization, but it is arbitrarily bad when we try to minimize this age of information. And even if we discount this energy cost, if we only just look at age of information minimization, even there it is arbitrarily bad, because you consider this update generation time. So this height denotes sizes, and so these are generation times. So OPT can transmit selective updates, and it can have a finite age of information, while this SRPT gets stuck transmitting these smaller updates without looking at their generation time, and hence it is arbitrarily bad. So sufficiency, I mean, when you have a lot of packets, you can discard a few packets, and still you can have a small age of information. It may not. So it can, but it may not if you do scheduling efficiently. So it may not, because for example, there are two updates that arrive in quick succession, and their sizes are very large. So you can actually drop one of them and transmit the latest one, maybe, and then you can get similar performance than, in fact, better performance than transmitting both, because it creates backlog in your network. Yeah, yeah, yeah. Yeah, yeah, you can do that. But again, the thing is, right now you're discarding a large packet, but the thing is, maybe next packet will not arrive at a very long time. So in those cases, it might make sense. Um, so I mean, this is what we will look now. So which update to transmit? So like just like two notations. So for update, this GI denotes its generation time, and SI denotes its size, right? And the thing is, GI is like generation time, which is fixed, but the size decreases as you transmit. So as you transmit with the remaining size, we denote it by SI of T. So at time T, the remaining size will be. So these two notations I would like to like carry from here. So which update to transmit? So you have, for example, you have these 4 updates, and so at this time T, you look back, and so this update J has been transmitted. Its remaining size is 0. So basically now your age of information is basically depends on this quantity, how old this packet is, because this is the latest packet at the monitor. So now to minimize this age of information, all old packets are useless. And so naturally, like we need to choose which packet to transmit next among the like newer update. And so the choice at this time is whether to transmit this update K, update L, or don't transmit. Wait for maybe next update. So, so which one is optimal? So let's consider this, see this with example. Now consider the simpler setting where we don't have, okay. So these, like it is obvious this update L is newer, but its size is larger. And at time T, you have certain known age of information. For simplicity, we assume that there is no energy cost. So out of 3 possibilities, the third one, whether not to transmit, that is ruled out. You should always transmit some update, and if a new update arrives, you can always preempt. So now which update to transmit, A or L? Uh, okay, so choice one. Let's try to begin to transmit update K. So you transmit it after some time, the transmission is complete, age of information decreases. However, this decrease is small because the packet was already old. Now you have at this time update L, you begin to transmit it. So again, you get some decrease in age of information, but again, this decrease is small because by now this update L has become older. So in contrast, what you can do is you can directly begin to transmit this update L. So it takes some time, but then the decrease in age of information is also large. So basically, now you have to compare these two, which one was better. So yeah. So let's just plot both these plots over one over the other. We see that if this area of B is greater than C, I mean, then it is better to transmit update L directly. And if this was the other way around, then transmitting first update would have been better. But throughout this, we assume that no update arrives in this interval. What if another update would have arrived? So in that case, what you can do is you can directly transmit update K and then update M, just leaving behind this update L. And in this case, you get that comparing, you get that this transmitting this older update was better. So what decision at time t is optimal? That will depend on future update generation times and sizes. So regardless of what you do, in worst case, it can always be suboptimal. So basically, instead of trying to find the optimal scheduling policy here, we are trying to find a causal policy which has least competitive ratio. So what is that? So competitive ratio is a metric to quantify the performance of causal policy, which policy that does not know future. So let sigma denote the sequence of all the updates and the update generation times and their sizes. So a causal policy does not know this. Now, for a causal policy pi, this cost pi sigma is the cost incurred by causal policy pi if the input arrives at per sigma. And this is the cost incurred by an optimal offline policy, which know a policy that knows sigma in advance, that is an optimal offline policy. So competitive ratio is basically the ratio of the cost of this optimal policy divided by the cost of optimal numerator is the cost of causal policy, denominator is the cost of optimal offline policy, maximized over all possible sequence of generation times and sizes. So this is naturally always greater than equals to 1. I mean, we showed already that it is always strictly greater than 1. But how small can it be? So we saw that this SRPT has unbounded competitive ratio because maybe the reason was it only looks at the sizes. Likewise, we can show that LCFS, this last come first serve algorithm, it takes decision based only on generation times. So this also has unbounded competitive ratio. This is easy to show. What about a policy which accounts for both update generation times and sizes? A most reasonable policy appears to be the following ready policy, that at each time t, for any update, fresh update that is generated after transmitted updates. So for every update I, it assigns a index that we are calling as grade. So this index is basically the ratio of the reduction in age of information that I would get if from now on I begin to transmit this packet without preemption, divided by the time it would take to completely transmit that state. Right? So how much decrease in age of information divided by the time to get that reduction. And you transmit the update with this largest gate, which gives you maximum reduction in age of information per unit transmission. So this appears a very promising candidate. However, it has some problems. So here you can preempt, here it is possible that a larger packet preempts a smaller packet just because it was slightly new. So it is possible that back-to-back preemptions may happen. A packet is under transmission, it is preempted by a newer one, which is again preempted by another one. And it is possible that this age of information might grow large, right? I mean, so this is it is difficult to bound its competitive ratio, basically. Uh, so what to do now? So basically, we need to fix this issue. If we fix this issue, maybe large updates does not preempt small updates. Maybe we can do something. So that is why we actually propose this algorithm that we call as SRPT plus, which works in like two parts, depending on the state of the system. If say update I is under transmission, then a new update is generated and you need to choose what to do. You basically follow SRPT. If the new update is generated, if it has a smaller size than the packet and the transmission, then you preempt the update and begin to transmit the new one. Otherwise, you continue to transmit uh, the packet that you were transmitting. Yeah, you just keep that new packet aside in the buffer. So this ensures that preemption never delays transmission completion. So the issue in previous thing is solved. And when no update is under transmission, that is previous update has like transmission has completed. You have a bunch of packets in your buffer. Now you have to choose which packet to transmit. Then you follow the greedy policy, basically, that we just discussed. So now with this small modification, what we get is that this greedy policy, when there is no energy cost, this greedy policy has competitive ratio, this SRPT plus has competitive ratio at most 3, right? But again, this is when there is no energy cost. The problem that we considered has energy cost. So naturally, see, the problem here is that this is where the packet is under transmission. So to minimize energy cost, you have to stop transmission at some point, like you transmit less. So here at this point, if you have a fresh update, what greedy policy was doing, it will always transmit some packet. If you have packet here, it will always transmit some of it. But if say this packet is offering me less reduction in age of information, then maybe we should not transmit it, right? So uh, what we do is here we introduce a threshold condition. So this accounts for the size of the update, the reduction in age of information that we would get, and also the energy cost. And based on that, it shortlists among the fresh updates that whether I should transmit it or maybe I should wait for another update generation, right? With this small introduction, like manipulation, we see that uh, like we are able to control this energy cost and show that even when there is no, even when there is energy cost, the competitive ratio of this algorithm is at most 5, right? So, any doubt until this point in algorithm or the result? Here we have a single source. This is the first part. Now I will come to the multiple source setting. Right now you only have one source, so all updates are from the same source. So a new update, if we transmit a new update, the old update is useless. But the new update size is large, then you may want to first finish transmitting this old packet and then transmit the new packet, maybe hoping that some smaller update is generated in future, so you may not need to transmit the newer update at all. Um, so yeah, actually, the thing is, if there are like kind of sub packets, if you're transmitting sub packets like of a bigger packet, uh, for example, in a video, like you can have a frame which is considered as a whole packet. You are transmitting it in chunks. Then maybe you can stop transmitting it at some point and discard it at the monitor, and when new packet starts to arrive. So because at this point, you know, in this setting, you know that if monitor is receiving a newer update, then the older update is not going to come because then it makes no sense. Um, yeah. And actually, all this that I'm like discussing, this makes sense in what this virtual reality example that we considered in first slide. So actually, it can be motivated. like you need to make some adjustments depending on the application, but this can be motivated. So we saw right now that this age of information is online scheduling problem. This is like it has this combinatorial flavor, and we saw this worst case like input where you have arbitrary update arrival times and sizes, and policies such as SRPT and LCFS has unbounded competitive ratio. This greedy policy is difficult to analyze or in some sense establish this guarantee. So what we did took this SRPT and greedy, which are by themselves not, we don't know if they will work. SRPT will not work for sure. Greedy, we don't know. We need to bound this performance, but it's difficult. But by taking these two combinations and adding a threshold condition, we get this SRPT plus, which has this competitive ratio. So this concludes this first part of the talk. Uh, any doubts, questions? Yeah. Yeah. No, I mean LCFS also makes sense. For example, if you are taking a queue where these sizes follow some memoryless distribution, you don't know the sizes up front, but you begin to transmit it, and the transmission completion takes is exponentially distributed. So there, if you get a new packet, if they have the size distribution is like kind of identical. So it's always better to follow LCFS. So it's not like LCFS does not make sense, but depending on the model, you need to change something. So here also we are taking, when we look at the reduction in age of information, that is accounting for the some kind of taking inspiration from LCFS also, because the reduction in age of information is maximum for LCFS. Um, so we need to adapt it basically. That is the point. Nothing else. So this is the a more general setting where we have this multiple sources trying to transmit to the monitor. Here we make some assumptions, so we don't take this just arbitrary arrival times sizes. Rather, we assume that they follow some fixed distribution. So this distribution can be different for different sources. It can be any arbitrary distribution, but for a source, this intergeneration times is follow one. And yeah, also the sizes. So there are like two differences. First is these sizes follow again any arbitrary distribution. For the distribution can be different for different sources, um, and also you don't know them upfront. So you have a packet, you begin to transmit it, and when the transmission completes, you know that the transmission has completed. So upfront you don't know the sizes when the packet is encrypted. Now at here, yeah. So size is unknown until completion, and so this problem we actually consider in two parts. The first is like when there is non-preemptive setting. So when you are not allowed to preempt. So as we just discussed. So so in this setting, we will consider the first the results and then the challenges for the preemptive setting. Okay. So at any time, at most one source can transmit. So this is a natural constraint that we have to. Um, and also there is a fixed transmission cost. So here we are, the transmission cost is incurred per packet which you transmit. So every packet that you begin to transmit, you incur this cost CL. And so the energy consumption is like proportional to the number of packets that you transmit. Right? So just to recall, so you have multiple sources. At each source packets, intergeneration time follows some fixed distribution. Their sizes again follow some fixed distribution. The sizes are not known upfront, and so when you transmit, one source can transmit at any time, and when you transmit, you incur a fixed transmission cost. Again, this cost can be different for different sources, but for a single source, every packet transmission has fixed cost. Yeah, so here the objective is to minimize the weighted sum of the average age of information of all the sources subject to a constraint on the total energy cost. So this WL weight for source L, this is the average age of information, this is the cost per transmission, this is the number of packets that you transmit per unit time for source L, and this is a fixed constant. So this cost, energy cost has to be less. Actually, we can also take the sum of these two. So the results and guarantees all are like same. Like in previous case, we took the sum of the average age of information and energy cost. Here we have just moved one of it in the constraint. But the thing is, even if we take in the objective, we have like exactly same guarantee that we will show. And here the problem is which source gets to transmit and which update the source will transmit. RL is the rate at which you transmit, the number of packets that you transmit per unit for source. And you need to transmit like which source gets to transmit and also which packet should. So here the related most relevant work that I would say like for single source with transmission cost was like considered in 2017. And here a new update is available all the time. So here the source can choose it, like that model, they assume that the source can generate update at any time instantaneously. So there you always know that when you have to transmit, you can generate a packet. And for this, they derived an optimal causal policy. This was for single sources. But for multiple sources, transmission cost has not been considered as much. And here the most relevant that we could find was where you have this, they consider discrete time setting. And the inter-arrival times and service, like this sizes all followed geometrical distribution, metric distribution. And for this, we derived causal policies with competitive ratio at most 4. But these are like limitations. They are fixing the distribution, geometric. And geometric has good properties. They are memoryless. Yeah. So in this work, we basically consider geometry like continuous time setting, where these distributions can be arbitrary, and also there is transmission cost. So for this problem that we consider, we propose a randomized scheduling policy, and for that we show that the competitive ratio is upper bounded as follows. Basically, to say this is independent of the size distribution, but it depends on the update intergeneration time distribution. So like for single source setting, you have in prior work we saw that they assume that update can be generated at any time. So if we assume that, this thing actually goes away. Even for, and also this quantity, this is at most 1 for these common distributions like exponential, uniform, Rayleigh, or rather like geometric. So the thing is, if we put here like geometric distribution, again we get the guarantee 4 that we have in prior work. So yeah, and for this policy that we have, this is actually kind of hard to avoid, but this is still the best that we have at this time. So this policy actually has like 2 parallel subroutines basically. First is like at source when packets are generated, the source decides whether or not this packet is worth transmission. So it's not about like when it is transmitted. So a source just keeps most relevant packet with itself. And the second is the scheduler decides which source gets to transmit. So how a packet is selected? Basically, at each source, whenever an update is generated, it is marked with probability PL. So this probability that PL is, it is found by minimizing an upper bound on the for this policy. And this actually takes care of all the different parameters, different for different sources and everything within that. And yeah, this is how the packets are marked. And a packet that is not marked is basically discarded. And yeah, so a packet is discarded with probability 1 minus PL, marked with probability PL. Now, when source L is selected to transmit, it basically picks the latest of the marked updates and begins to transmit. If it does not have a marked update, it won't transmit. But then how a source is selected to transmit? So again, for each source L, we define this probability QL of picking that source. This QL is basically proportional to like the frequency at which the source gets a marked packet. So like basically the number of packets that are generated, the rate at which the packets are marked, it is proportional to that. And it is actually, it depends on the PL, packet marking probability. And this QLs are actually normalized such that they're equal to 1. So at any time, at most one source is selected. One source L is selected with probability QL. So that source now begins to transmit the latest marked packet. Yeah. Any doubts with the policy? So basically the policy has two parts. One, a source decides whether a packet is worth transmitting or not. Then the scheduler decides which source to transmit. So this is how both of these work together. So this update selection is actually important to minimize, like, critical to manage the transmission, because a source can always be transmitted, selected by the scheduler, but if every time it gets to transmit, if it begins to transmit, there will be very large transmission cost. And this source scheduling basically controls the frequency at which the different source gets to transmit its market. So we just saw this multiple source setting, and with arbitrary size and intergeneration time distributions, fixed transmission cost. And for this, we saw that this two-stage randomized policy has competitive ratio, which is independent of the sizes, and is at most 4 for common distributions that has been actually anyway analyzed in the past. So this, until this point, this appears good, but again, what is the catch? So the thing is, so this first part, this is good for certain distributions, but when, say, for example, heavy tail distributions, this can be large. This bound is actually depends on the update arrival time distribution, and it can be large. And the second is, we got this independent of this size distributions because we made this non-preemptive assumption. So what happens is when a optimal policy begins to transmit a packet, because it also does not know the size of the packets, so it can't improve its performance beyond what we do in this algorithm. And the effect of this size distribution is same on both. So when we take their ratio for competitive ratio, we get something that is independent of the size distribution. Any doubt until now? Yeah, I mean, this is a simplifying assumption to a large extent, I would say. But yeah, I mean, this is something that we would like to maybe at least like take it to the level where at least we consider dependence on just previous update or something like that. But yeah, I mean, this is all that I would like to say at this point. Yeah. So why is this competitive ratio dependent on GL? This update intergeneration time distributions. So what we do is actually we take these different factors for the sources, the generation rate, mean sizes, and the transmission cost, and from them we derive what should be the optimal intergeneration time of packets. So for example, when you have the choice that you can choose when update to generate updates, So what should be that difference between these successive update generation times? So we find that, but we don't choose when updates are generated. So we basically try to transmit packets that minimize variance around that generation times. And this is how we get uh, the guarantee. But again, so doing this, minimizing this to zero is certainly like not possible for general distributions. Um, but what an offline policy can do, it may have zero variance because it knows when the updates are generated. For certain distributions, it may be possible. Um, so that is why making it dependent on, like, competitive ratio is dependent on, uh, basically we need better bound on this OPT's cost to make this guarantee, competitive ratio guarantee independent of size, generation time distribution. Now, so why this is independent of size distribution? Because basically uh, this age of information depends on these latency of transmitted updates and intergeneration time of transmitted updates. So basically, so updates that you transmit, how much time they get and how much apart they are themselves in time. So if you transmit updates that are very close, because of their sizes, one will have to wait. If two updates are generated very close to each other, then other will have to wait for the completion of first packet. So its latency will be large. So basically these two things are inversely related, and these two together control this age of information. Um, so impact of this transmit, like, intergeneration time distribution, we just saw. So because of that, we, like, this is still appearing in the competitive ratio guarantee. If we take, but if we take this appropriate intergeneration times, then latency primarily, so for example, if they are sufficiently separated in time, the generation times, then the latency is very close to the size of the packets themselves, because then it does not have to wait for the completion of previous transmission. So I mean, just giving this brief, like, idea, but yeah, I mean, there is like more complications to it under the hood, but yeah. So in non-preemptive setting under proposed policy, so basically this average size is equal to the mean of the size distribution, and hence it is like latency is compared to this, that of OPT, and we get competitive ratio independent of the size distribution. But but this is all for non-preemptive setting. What about, like, what about preemptive setting? So let's say we have these 4 packets arriving at these times, and this update 1 is transmitted and 4th is transmitted, right? So this is the time between successful transmissions, and this is the latency for the packet. So latency for this packet is this one, this packet is this one, and this is the time between successful transmissions. Something that we just discussed in previous. Now consider some, like, weird distribution like this, where the arrival times, like inter-arrival time, can be arbitrarily close to 0, or it can be very large. So here, if you are considering this preemptive setup, where you can preempt the update in the transmission, so what a policy can do? Consider the setting where you don't have energy cost. So what a policy can do, it can just, whenever a packet is generated, if you begin to transmit it, if it takes more than epsilon time, you know that I will have to wait for a very long, you just drop it. And if a newer update is generated, you begin to transmit that, right? So in this way, the time between successful transmissions can be arbitrarily small, because see, if a packet can have a very small size, with probability half, and the packets are arriving in quick succession, if you keep dropping them in epsilon time units, you will certainly find some update that gets through very quickly. So this can be minimized, and simultaneously, if you follow this strategy, then the packet that is completely transmitted will certainly have latency at most epsilon, because if it is more than epsilon, you just drop it. So because of these two, which can be arbitrarily small for OPT, which knows the arrival times, uh, you get a very poor bound on the cost of OPT. And yeah, and for causal policy, it's not obvious when to preempt because it does not know the next packet arrival time. You can't just preempt it upfront. Um, and also, like, the policy that we have, actually this needs to work for all these arbitrary distributions. We are not utilizing the structure of the distribution because it has to be for arbitrary distribution. If we know the distribution, for example, if it is exponential distribution or something, then we can actually improve it. Uh, but for without knowing the distribution structure, it is difficult to actually determine when to preempt. And hence it is hard to bound this competitive ratio when we are in preemptive setting. However, as I just said, if you have this nice size distributions like exponential, uniform, etc., where you cannot minimize the time between successful transmissions just by preempting a tape. So for example, if the size is exponential distributed, if you are transmitting a packet and a new update is transmitting a packet and a new packet is generated, even if you preempt the older packet and begin to transmit the new one, the time that you need to successfully transmit one update, that does not change with preemption. However, the newer packet will give you more reduction in age of information, that's true, but the time between successful transmissions can't be minimized that way. So the first issue here, uh, this is ruled out for such nice distributions. And again, the latency part, this can be approximated with the other costs that you are already incurring because of the intergeneration time distribution, basically. So because of this, you can actually come up with some bound that is not very poor. And in fact, we did that. And for such distributions, we showed that this competitive ratio for the same proposed policy, which is non-preemptive. Even in the preemptive setting, given the distribution has this nice properties, it is independent of the size distribution. I mean, it still depends on the update generation time distributions, but independent of the size distribution. And this, if you compare to the non-preemptive setting, it just differs by 2. Yeah. So for single source setting, we had competitive ratio 3 and 5 for when we had this no energy cost and energy cost. Here we have again 3 plus something and 5 plus something for non-preemptive and preemptive setting. So any questions at this point? So with yeah, so we are in the final slide. So basically, we consider this online scheduling problem where we have to minimize both this age of information and energy cost. And we saw the challenges because you need to both choose a subset of packets to transmit and then basically choose which one to transmit. And for the single source setting, arbitrary arrival times and sizes, we saw that this SRPT, LCFS, don't work well. And but this SRPT, it has this competitive ratio at most 5. For multiple sources with arbitrary distributions on arrival times and sizes, we saw that randomized policy is independent of this size distribution. Now, the next challenge here is to make them independent of update arrival time distributions, which we like to think of. So we don't know if there exists a policy which is independent of these distributions at all. Yeah, so the first part that we considered, so this like details can be found in the recent paper in performance evaluation. For the simpler setting where we have this stochastic setting and some assumptions on the sizes that appeared in this infocom, and what we discussed, the tunable energy consumption. So there you control the rate at which you transmit packets, and accordingly you draw power. So that is again appeared in this IEEE journal on set areas in information theory. Yeah, and for the multiple sources, that again appeared in the same journal recently. Yeah, so that's all from my side.
Thank you for an informative talk. Are there any questions? Any questions from online audience? Okay. Thank you.
Although you're modeling partial updates, but the partial updates don't seem to be useful because unless the entire packet reaches out
Yeah.
there, it's of no use, right?
Yeah.
So, but in practice, partial updates could be useful.
Yeah, depending on application. Yeah.
Any questions? Okay. Let's thank the speaker again. And outside coffee hut, we have arranged for refreshments. Please help yourself there.